Hi, in this video I'll teach you what is the Cramer's rule and how does that solve a system of linear equations. Well, let's start with the assumptions that we need. So we are assuming that first the coefficient matrix is an n by n square matrix. And determinant of A is non-zero. In other words, it is invertible. That means that AX equal to B has unique solution. Now we want to find that unique solution. Remember, X is x1, x2. It has n variables, so we have to find n numbers. So the Cramer's rule says first form these matrices. Form A1, A2 up to AN. What are these guys? Where AI is the matrix obtained by replacing, so you take out the ith column of A and replace it by the vector B, replacing ith column of A by vector B. So A1 means that you take out column 1 and put vector B as the first column. A2 means that put vector B as the second column of matrix A and leave everything else as before. Okay, so that's the first thing. Then the second thing is that find determinant of these guys. Well, determinant of A also is required. Find determinant of A, determinant of A1, determinant of A2, and up to determinant of AN. So if you have 3 variables, you need to find 4 determinants. Determinant of the coefficient matrix, determinant of A1, A2, and A3. Now, the last step is that the unique solution has the following components. So the first component of the solution is a determinant of A1 divided by determinant of A. X2, the second component of the solution vector, is determinant of A2 divided by determinant of A. And this goes up to xn, which is determinant of AN divided by determinant of A. So you find just these determinants and then divide all of them by determinant of A, and those will give you the components of this unique solution. Okay? These 3 steps are called the Cramer's rule. Okay, so let's just do some examples. use the Cramer's rule to solve the given linear systems. Well, what do we need? We need to know what is A. It is 1, 2, negative 1, 1. And we know what is vector B. So it is 2, 1. From there, I can make A1. What is A1? A1 is you put B as the first column of A, so it will be 2, 1, and leave the second column as it is. And for A2, you replace second column of A by B, which is 2, 1, okay, 2, 1. Here's 1 and negative 1. Now, find determinant of each one of these guys. Determinant of A is 1 minus negative 2. This is 3. Determinant of A1, here's 2 minus 2. This is 0. Determinant of A2 is 1 minus negative 2 is 3. Very nice. The first component, here the first component we denote by X, and the second component we denote it by Y. The first component is determinant of A1 divided by determinant of A. This is 0 divided by 3. This is 0. The second component is determinant of A2 divided by determinant of A. So this is 3 divided by 3, which is equal to 1. That's how you use determinant, or what's called Cramer's rule, to find the unique solution of the system. The unique solution is when X is 0 and Y is 1. How about this one? Okay, A is 2, 1, 0, 1, and negative 2, 1, 4, negative 3, 2. We have to make sure that this matrix has a non-zero determinant. Here, when you try to find the determinant of this guy, this will give you 0. Try it. You will get 0. It means that, well, first of all, the system doesn't have unique solution, and the Cramer's rule cannot be applied here for this system. Cramer's rule works only when the coefficient matrix is a square matrix and it has non-zero determinant. And you can see why, because we are going to divide this determinant of A1 up to An by determinant of A. You cannot put 0 in the denominator. Okay, so this doesn't work. Cramer's rule cannot give you solutions for that system if there is any. Okay, how about this one? Okay, we have A. Let me write it down here. We have matrix A, which is 2, 0, 1, 1, negative 2, 1, 0, negative 1, and 1. Matrix, the vector B here is 3, 6, negative 3. Okay, then we have to form A1. Oh, by the way, we checked this matrix in another video, and we know that determinant of A is 3, negative 3. We now need to know what is A1. A1 is when you put B in the first column, so 3, 6, negative 3, 0, 1, negative 2, 1, negative 1, 1. A2 is when we put B in the second column, so this will be 2, 1, 0, 1, 1, 1 is there, so this will be 3, 6, negative 3. How about A3? A3 is when we plug in the column B in the third, vector B in the third column of the coefficient matrix. So this will be 1, 0, and 0, negative 2, negative 1. Here this will be 3, 6, negative 3. Well, now we need to find the determinant of each one of these guys. Determinant of A, this is negative 3. Determinant of A1, we can expand along the first row. It has at least 1, 0. This will give us 3 times negative 2 plus 1. This is negative 1. Minus 0, doesn't matter what is the determinant of submatrix, and 1 here times negative 6 plus 6. So that is negative 6 minus plus 6 is negative 12, and that gives us negative 15. How about determinant of A2? Determinant of A2, expand along the first column. This will give us 2 times 6 minus 3 is 9, minus negative 3 is 9, minus 1 times 3 minus negative 3 is 6. The last entry is 0. And this is 18 minus 6, which is 12. How about determinant of A3? Well, this guy gives us, let me just write it here, zoom in a little bit. This one gives us 2 times 6 minus negative 6, this is 12, plus or minus 0 times something, plus 3 times negative 1 minus 0. So this is just negative 1. And when you compute that, you get 24 minus 3 is 21. Very nice. Now, the first component of the solution, which is x, is going to be determinant of A1 over determinant of A. This is negative 15 over negative 3, which is 5. Y is a determinant of A2 over determinant of A. This is 12 over negative 3. This is negative 4. And Z is determinant of A3 divided by determinant of A, which is 21 over negative 3, which is negative 7. So the system has unique solution. I do write it this way: 5, negative 4, negative 7 is the unique solution of the system. Well, Cramer's rule is good when you have a good tool of computing determinant, and it only uses determinant to find a unique solution. And the good thing about this rule is that when you're interested only on one of these components, definitely Cramer's rule is what you need to use to find that component of the unique solution.